Let's look at the following problem. This is a tricky problem, so please watch until the end. Two small, sticky, putty balls, call them ball 1 and ball 2, with the same mass move under the influence of gravity with acceleration given by that. These are the initial conditions, meaning for ball 1, its position vector at t equals to 0 is given by that, its velocity vector at t equals to 0 is given by that. For ball 2, the position vector at t equals to 0 is given by that expression, and its velocity at t equals to 0 is given by that expression. Determine the position vectors of ball 1 and ball 2 for all times t greater than 0 second. Note, at all times. So let's do ball 1. Its acceleration is given as minus 9.8 k hat meter per second squared. That means its velocity vector at any time t is given by the following expression. You have to integrate the acceleration vector with respect to time. We note that the acceleration vector is a constant, so that means integrating it will get you the following result: minus 9.8 t k hat plus an integration constant, call it c1, which is also a vector. It's a constant vector. We note that at t equals to 0, the velocity vector for object 1 is given by that expression. So the first term goes away because at t equals to 0, the first term is 0. And since we know v1 at t equals to 0 is 7I hat plus 3j hat, and that is quite simply the integration constant vector c1. So we have a complete expression for c1, namely 7I hat plus 3j hat. So that is the velocity vector of ball 1 at any time t. Now let's proceed to determine its position vector, r1t. Now we know in order to get that, we need to integrate the velocity vector as a function of time with respect to time. So let's substitute the expression. It's minus 9.8 t k hat plus 7I hat plus 3 j hat. Integrate that with respect to time. Integrating t will give you t squared over 2. So overall you get minus 4.9 t squared k hat. Integrating the second term, which is just a constant 7, you get 7t I hat. And the third term is 3t j hat with an integration constant. Let's call it d1, which is also a vector. It's a constant vector. We are given an information to determine this d1. At t equals to 0, r1 is given by that expression. So substituting t equals to 0 here, and equating that to 7i plus 4.9k hat, we'll be able to find the vector d1. r10 is 7i hat plus 4.9k hat. On the right hand side, it is just d1. So we have the expression for the vector d1. Substituting in here, we get 7i hat plus 4.9 k hat. So let's rewrite this expression. The position vector of ball 1 at any time t equals, there are two i's, let's combine them, 7t plus 7 I hat. There is that j component, 3t j hat, and there is this k hat term, so plus 4.9, 1 minus t squared k hat. Now let's repeat for ball number 2. Now we know the acceleration is the same, namely it's minus 9.8 k hat meter per second squared. That's given right there. So its velocity vector at any time t is obtained by integrating that term, and that's going to give you minus 9.8 t k hat, we're integrating with respect to time, plus an integration constant, a vector, let's call it c2. However, we know at t equals to 0, its velocity is given by that expression. So minus 7I hat plus 3j hat is quite simply that constant vector c2. So let's write it over there. Minus 7I hat plus 3j hat. So that is the velocity vector of object 2, or ball 2 at any time t. Now the position vector of ball 2 at any time t, and that is just an integration of the velocity vector at any time t of ball 2 with respect to time. So let's do term by term. Integrating the first term with respect to time, you're going to end up with minus 4.9 t squared k hat. Integrating the second term, minus 7t I hat. Integrating the third term, 3t j hat, plus an integration constant, which is a constant vector d2. However, we know that at t equals to 0, r2 is given by that vector. So let's write that down. 49 I hat plus a 4.9 k hat is your vector d2. Plugging this inside of that, we get a general form for that vector r2. Let's record that expression here. Let's write down the I term. There are two, 1 and 2. So that's going to be 49 minus 7t I hat. There is only one term for the j hat, so it's plus 3t j hat. And there are two k hat terms. So plus 4.9, 1 minus t squared k hat. We note that the y components and the z components of the position vectors for these two balls are the same. The x components are generally different. Let's see if they can be made to be equal. So 7t plus 7 equals 49 minus 7t, which would give us t equals to 3 seconds. What that means is when t is less or equal to 3 seconds, their individual position vectors are given by these expressions. At t equals to 3 seconds, they stick and they move together. And the I component of the position vector becomes 28 I hat, because that is the time when they collide and stick together, and beyond that they will move as a single particle. So for t greater than equal to 3 seconds, r1 equals to r2, and that is 28 I hat plus 3t j hat plus a 4.9, 1 minus t squared k hat. So that is the expression for the position vectors of these two balls for t greater or equal to 3 seconds. And that solves the problem. Thank you for watching.